part 4 regards to maximum earth fault loop impedance. So in here, this particular section, what we have is that formula in part 4 rearranged in a much better way, to be quite honest, because it looks more like Ohm's law. That's voltage. Remember, C min is allowing for, is this 0.95, it's 95%, because it allows for voltage variations, which is what it says here. And then we divide by current, so this is volts divided by amps, gives us ohms, and these are how all the ZS's are calculated in the previous tables that we've looked at. So IA, where does that come from? Well, it's the current that causes operation for the time. That's what it says it underneath. So if we scroll forward and let's take a look at this particular one here. So this is a BS88-3 fuse. So this is a cartridge fuse. On what we've got on here then is a logarithmic graph, so hence they're not equal spacing. So up the side here you've got time in seconds from 0.01, 02, 03, 04, 5, 6, 7, 8 to get to 0.1 of a second, 0.2, 0.3, 0.4 to 1 second, 1, 2, 3, 4 till you get to 10 seconds, and it goes right the way up to 10,000 seconds. It's quite a long time. And across the bottom you've got the fault current. So what you've got along here, these are IAs, effectively, whichever IA you wish to go for the respective time that you want it to go for. So again, it's logarithmic, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You get the idea, to 10, 20, 30, 40, 50 to 100, 100, 200, 300, 400, 500, 1000, and right to 10,000. And these are the respective fuses laid out here. These aren't the only ones. If you've got fuses that are bigger than these or not listed on here, then it's back to the manufacturers for that information, but the regs do print out the vast majority of what you're probably going to use. So 5 amp up to 100 amp on this particular fuse system shown here. So how do we use this then? Well, it's quite good at finding disconnection times for the amount of fault current, or vice versa. If you know the fault current or the time, you can work either direction. So my question would be, how many seconds are there in an hour? Well, so we're all thinking, right, it's 3,600, because that's what it is. So up here, so what we can do, there's 1,000, 2,000, 3,000. Now 3,600, because it's not a linear graph, it's not equal spacing, halfway is not half. Halfway between two lines is about 0.45. So actually 3,600 is nearer the next line than it is the middle. So 1,000, 2,000, 3,000, 3,600 is roughly around there. In fact, if you scroll across, when you look across, you'll see this line here, because this relates to 1 hour. So this line is 1 hour, 3,600 seconds. And what it allows us to do is we can then look from the respective fuses, we can look down and basically take this first one here, and we can scroll down, look down. This is where you start to see lines, because you've got to make sure you're looking right. And we can see it's bang on that line there. So this is for the 5 amp fuse. So that's 1, 2, 3, 4, 5, 6, 7, 8 amps. So basically what that means is that BS88-3 fuse will hold for 1 hour if 8 amps passes through it. So the IA, so if our disconnection time was 1 hour, which it obviously it clearly isn't, then the IA for that device at that particular time would be 8 amps. So that's what it's quite good at. So clearly we don't want a fault to be 8 amps, because it would sit there and hold for an hour, which basically means the place may well burn down. So that's not what we want. And the sort of fault that would cause that obviously would be overload, which we try and design out in the first place. So we don't, it's quite difficult to use, but it gives us that information. So what they provide over here are the basic times listed in the book, and some that are not so used very much, but we have them. So there's our 0.4 of a disconnection time and our 5-second disconnection time, because these are fuses, and the way fuses work are the more current you put through them, the quicker they will disconnect. So if you look at the 5 amp fuse, that same one, obviously we knew it in 1 hour, it took 8 amps to make that go in 1 hour. If you want to go in 0.4 of a second, you need 22 amps. If it needs to go in 5 seconds, then it takes 15 amps is all you need to do. So therefore, the respected ohmic value of the circuit can vary for each respective disconnection time that you may have. Therefore, ZS's do change. Let's look at a circuit breaker. So this is a BSEN 60898, or an RCBO to those British standards as well, but this is a Type B circuit breaker. And you can see the graphs are very different on this particular one. In fact, all circuit breakers look like this. So if you see a graph shape in Appendix 3 that looks like this, you know you're looking at a circuit breaker. So what you can see a distinctive curved line, and then it goes vertical. The reason for that, because there are two components inside a circuit breaker that make them work. One is a bimetallic strip, which is thermal related, which is curved, which is very similar to what the fuses are, because fuses are thermal devices. So this part here is the thermal part of the circuit breaker, which would work on overload. And this vertical part here is the magnetic part of the circuit breaker that's going to make that part go. And that's the bit where it's most effective. And this is why circuit breakers tend to outperform fuses on the whole. So we can look here on the right hand side, we have the table given to us, and we'll note now we've only got one column for the currents because the times now are 0.1 to 5 seconds. And the reason for that is because circuit breakers are good and they will basically disconnect in 0.1 of a second, providing you meet that threshold of current. So looking at the 6 amp this time, you need 30 amps. And if you have 30 amps as a fault current, it will disconnect in 0.1 of a second. Unlike a fuse, if you put 60 amps through the 6 amp circuit breaker, in a fuse that would get quicker. In a circuit breaker, it will not. It will just still go in 0.1 of a second. So the more current you put through it, providing you stay within the braking capacity, the fuse will still disconnect in 0.1 of a second. However, interesting point to note, if you go 29 amps, so 1 amp under the 6 amp, if we look down here, so 29 amps, you can't get accurate, but you know it's just below that line somewhere, so it puts it there. And if we look across, that is over 10 seconds to disconnect. So when they work, but you go even 1 amp under that threshold of the current in the table, and they will disconnect really slowly in comparison. So 30 amps, they go in 0.1, 29 amps, all of them go over 10 seconds. So you're probably looking at 12, 13 seconds for those protected devices to go, which is not good because it means the cables now are overloaded for that period of time. So the ZSs that are provided in the regulations from table 41 onwards, they're all based at 70 degrees, which is what we've been saying. So one of those working temperatures. However, when you're testing, you're unlikely to be testing the conductors when they're at 70 degrees because you're putting them first into use. So you're commissioning at this point. So they will be at whatever temperature the room happens to be. So typically, we sort of take about 20 degrees, roughly about that is what we sort of tend to take them to be. And therefore, we can apply a correction factor to all the values in the table to check with your on-site version. So, and the multiplier they provide is 0.8, and that's where this formula here comes into play. So ZS is equal to, or less than or equal to, 0.8 times Ohm's law ultimately, which is voltage divided by IA. So remember, that's the bit how they make the ZS, and then they're saying to correct it for temperature, to bring it more realistic, multiply them all by 0.8. So 0.8 is quite a good factor. And actually, if you use your on-site guide for verifying the maximum ZSs of circuits, all the values in the on-site guide have already been calculated and multiplied by 0.8. So they're much more user-friendly for on-site checking to see whether your circuits pass or fail for disconnection times. So interesting point to note is this regulation here, because it's basically saying where you have an RCD used as additional protection or to meet the requirements of disconnection times, then it has different disconnection times for the RCD itself. Therefore, you don't need to look at the previous tables. It's what it's saying is go and look at table 41.5. And if we just quickly go over the page, 41.5 is under the TT section, but this now gives you the ZS values for non-delayed RCDs, which is the vast majority that you would install. So for a 30 milliamp RCBO that you might have put in on a circuit, then the maximum ZS now is 1,667. That alters your maximum ZS for circuits.